Hello everyone. In this video, we are going to start our first Solana program, which is going to be a fairly simple one. So it's going to store a count value inside its state, and it will have 4 instructions. They will be increment, decrement, update, and reset. Depending on what the user wants, we will adjust the state accordingly. In front of me, I have an empty code editor, so I will create it with you guys. Let's start with cargo init. So it's going to create cargo project. We are going to name it counter, and I'm going to provide --lib so that it's going to have a lib folder inside. So let's take a look at the content. It's an empty cargo project, which is what we actually need in Solana's case. So first of all, I'm going to open up cargo toml and just copy and paste my dependencies. So these dependencies are specific for Solana's case, and as you can see, these are Solana program. This Borsch is what we are going to use for serializing and deserializing the data. Once we are done with the imports, we can just go ahead to lib.rs and adjust the imports. So in order to save time, I will just copy and paste the imports as well, and I will provide you this underneath the video so that you can also copy and paste without worrying about content. What we care about actually is defining the state. It is a bit different in Solana's case rather than the other blockchains. The smart contract that we are going to implement, so it's referred to as program in Solana, they are often stateless. Rather than storing the state inside the smart contract, we are going to define an account, and this account is going to be in charge of storing the actual state. Let's start with a struct. I will call this counter account because, as I said, this is an account. This is not stored directly inside the state. Just like what we have discussed, it's going to be a U32 variable. It's going to store a counter inside. Let's also add our derived statements. Derived debug is something we are used to from Rust, but in Solana's case, we also need to serialize and deserialize this data. So for that, I will derive for serialize and deserialize as well. And actually for our simple case, this is the actual state we are going to store, and we can just move ahead to the instructions. So for instructions, to keep it more clean, I tend to open up a new file and call it instructions, so that it will be a separate logic. It will be more modular. For this case, I will also copy and paste the import so that we will save some time. And as I said, we will have 4 instructions. So they are going to be enum rather than struct because only one of them can be selected at any point of time. Let's call this counter instructions. As I said, these are increment, decrement, update, and reset. So for our smart contract, these are not going to take any arguments apart from the update, because update all needs to get value inside of it. So to keep things more clean, actually, I will create this as a separate struct. So it's not that necessary in this case, but if we had a complex struct, it would be much better if we implement it like this. So inside the update, I will provide this update arc. And also we need to have the derived statements in here also, which are debug, Borsch deserialize, and Borsch serialize. So we are going to actually see what they are doing in the next video, but for the time being, let's just keep it like this. Now, the only thing we need to do is unpacking this instruction. So they are going to come to us with an encoded state. So we need to get them in a human readable form so that we can do operations on them. And in order to do that, I will implement for counter instruction, I will implement an unpack function. Let's make it public so that it will be reachable from lib.rs. So let's call it unpack. So this unpack is going to get an input. It's going to be of type U8 vector. It's going to return a result, which is going to be self or program error. And let's add this mod to librs so that we will see our errors in case we have any. Yeah, just like this one. Since we didn't have an return statement yet, it's okay to have this. So as I said, we are going to get a U8 array, which is a bytes array, and we need to unpack this into a human readable form. And for that, we are going to separate it into a variant and rest. I will try to split the input with split first. And in case it's not okay, we couldn't split it, I will return this program error saying that it is an invalid instruction data. But in case we have a variant and a rest, I'll return an OK response, and inside I will have a match of the variant. If it's a 0, we will do a self increment. If it's a 1, we will do self decrement. If it's a 2, we will do self update. And for the update, we have the arguments. So we need to give those to the lib.rs as well. And for that, I will do try from slice. And I'm going to give the rest, because the rest contains the actual update arguments in case we are getting an update request. Then I will just unwrap it. And similarly, if it's a 3, I will do self reset. And in case it's neither of these values, I will just do an error statement. And I will also call this invalid instruction, just like what we did in the line 19. So it's giving us the error because we have a unmatching parentheses. The unwrap needs to be inside this update. And now actually we are ready, but there's only warnings because we are not currently using the imports that we have implemented. And in the next video, we are going to actually have a process instruction function that will use all of these imports. So hope to see you in the next one.